Good morning, everyone. Good afternoon, good evening, wherever you may be. Hope you and your family are staying well. Thank you for attending this morning's webinar hosted by the San Diego IEEE Circuits and Systems, Electron Device, Microwave Theory and Techniques, Antenna Propagation, and Solid-State Circuits joint chapter. We are absolutely delighted to have Dr. Devendra Das Sharma from Intel to present a talk on PCI Express 6.0. So just a brief logistics. So we will have a Q&A halfway through the presentation and then at the conclusion of the webinar. If you have questions, please type them into the questions panel at the lower right corner of your WebEx screen. So I guess let's move on to the main event. So Dr. Das Sharma is an Intel Fellow in the Data Platforms Group and Director of the I/O Technology and Standards Group at Intel Corporation. He is responsible for delivering worldwide critical interconnect technologies in the Peripheral Components Interconnect Express, or in other words, PCIe Express, Compute Express Link, Intel's Coherency Interconnect, and Multi-Chip Package Interconnect. He is a key driver for external standards for PCIe and CXL and internal proprietary interfaces as well as implementation. So he joined Intel as a technical lead in the Advanced Components Division. Previously worked at Hewlett-Packard, developing server chipsets. Extremely well published as an inventor and a frequent keynote speaker, invited speaker. And very involved in the PCIe SIG board. Anyways, we are absolutely delighted to have Dr. Das Sharma come here and present at our chapter, and appreciate you stepping in as a distinguished lecturer this morning. Thank you.
Right. Thank you, Alvin, for that introduction, and greetings, everybody. I'll be talking about PCI Express 6.0. A low latency, high bandwidth, high reliability, cost effective. I know it's a word mouthful, but it's true for each and every one of those attributes interconnect with when we move to 64 gig PAM-4 signaling. So here is the agenda for today. It's fairly packed agenda, and I'll pace things accordingly. First, I'll go through the introduction to PCI Express and broadly the class of what I call the Load-Store Interconnect. I'll assume that different people have different level of understanding as far as interconnects are concerned, so I might go to some of the basics there and then quickly talk about the main topic here. I'll also talk a little bit about how PCI Express has evolved in terms of the data rate. Then I'm going to start phasing into 6.0 and talk about, in general, before we do a technology transition in PCI Express or any of the other external standards that we are, or even internal standards, right, that we drive. So I'm involved deeply with PCI Express and CXL. We basically look into what are the key metrics, what are the requirements. It's not that we come up with it right at then and there. We know that, but we basically put it next to us and say, okay, here are the guardrails for the technology. These are what will dictate how the technology evolves. So we will talk about those. What are the guardrails going into PCI 6.0? It's not, you cannot change a bunch of things because as we will see, these things evolve in a fully backward compatible manner. Right? You do want to make sure that the entire industry, the entire ecosystem comes along with you. We're then going to go through some of the basics, and people here would be very familiar with them, but just to talk about the philosophy, which is, what is PAM-4, what are the error assumptions, what are the characteristics, how do we get around those, like with error correction detection. We'll talk about the forward error correction, or FEC, cyclic redundancy check, or CRC, and retry. Then we'll talk about PCI Express. So both of those are applicable for the PCI 6.0, and then the flit mode that we introduced in PCI 6.0. Then we are going to go back to the key metrics and requirements that we had laid out and effectively do a scorecard, right? How well are we trending? How well are we doing? And then finally, I will conclude. So that's the agenda for today. As always, as Alvin said, if you have questions, please type them in. Probably take some some questions at an intermediate point during the talk, and then take the rest after the talk is over. So, stepping back and looking at taking a system level view, right? What does a cloud computing landscape look like today? What does a data center look like today? Whether it is the data center, whether it is the edge, all of them are using pretty much the cloud infrastructure. So this is a fairly representative sample. It's just that if it is data center, it's like a much larger in scale. If it is on the edge, it's a smaller scale deployment. But you see some pictures there. I put that these are like huge multiple football fields style buildings, right? Inside, right, what you have is something that pictorially looks like this. What you see here is racks of servers, and there will be a rack in a row that's typically called a pod, and you've got pods and pods and pods of these servers spread throughout the data center, right? So whenever you are doing something, you're Googling something, or whether you're looking up somebody in Facebook or what have you, right? Pretty much that's where it is going, right? And that's where you're getting your service from, or you're downloading a movie, right? I mean, that's pretty much where you're going, either there or at the edge. Sometimes they will try to do that service. Now, within each of the rack, as you can see here on the picture here on the left side, Alvin, I'm assuming you can see my cursor moving.
Yes, I can. Thank you.
Yeah. Okay. Sometimes I don't know, some platforms you cannot see the cursor. So thank you. So as you can see this is that rack, right? And you can see that it is connected through some wires. We'll talk about that, and interconnects are about those wires. So the green ones are what we will talk about. But then within each of this rack, right? So this is like if you open up a rack, you basically have what are known as chassis or drawer, right? And each of those drawers have basically servers inside them. And the servers inside them, again, there are interconnects, as you can see here, but pretty much it is what we'll talk more about that as LoadStore IO. And then you're going to have some kind of a top of the rack connectivity using networking semantics. So you're going to have like every server has got like a NIC card today, and based on that NIC card, you basically connect to the top of the rack. From the top of the rack, you're going to connect to a set of switches. Then on top of that, you're going to connect to another set of switches. And depending on the distance, you move somewhere here from pretty much copper to optical, because copper can travel only maybe 2-3 meters, and optical you can of course go longer distance. But there are different trade-offs, right? Power, performance, cost, all of that. So you got to effectively think of it as you got a hierarchy of connectivity, right? You got, and we are going to see a picture of the server here. Effectively, you got CPUs. Typically, it's very common to see people have like a 2 CPU sockets connected through some kind of a cache coherency link. You're going to have a bunch of IO devices, which we will talk about, like SSDs and what have you, right? Even networking card by itself is a IO device in there. And then from there you go using some kind of a networking connection. Some of the innovations that are happening in this LoadStore world is basically moving that IO connectivity from inside this chassis to across the rack. Today's talk is not focused on that. That can be a different talk, but it's around things like Compute Express links, where it is going beyond a node into a sub-rack and a rack level. That's where you're going to see this IO, which is PCI Express based IO that we will talk about, is moving there. So fundamental paradigm here is that you've got a lot of components here, right? And you've got a lot of resources here, whether it is CPUs, whether it is memory, whether it is devices, all of that, right? Accelerators, you've got all of these. The key here is how we connect them all together dictates the efficiency, right? And if you look the entire data center as a computing entity, the interconnects will be key to driving that warehouse scale efficiency. You need to, as long as you need to make sure that what is the semantics that is traveling across, and we'll talk a little bit of that today. This is my taxonomy. of different types of interconnect, and I'm going to put them into two broad buckets. Okay, of course, you can start subdividing them into many different categories, but we'll talk broadly about the characteristics and also talk about what are the trends, right? So this is the picture that we saw, different representation. Broadly speaking, right, I categorize the wired world, right? In other words, things that are running on a physical wire, right, into two types. The networking, which is the latency tolerant, and the load-store IO, which is latency sensitive. And it comes from the, basically these two attributes are coming from the type and the scale at which they are deployed. So if you look into the networking, it has to scale at a data center level, right? As you can see, right, I mean, the scale of networking, it goes throughout the whole data center. So by definition, it has to be tolerant of the latency. It's not like a load storage. It's not like a CPU which is a read and then it's waiting for something to come from the other end of the data center, and you're going to time out 20 times over. So it's tolerant for latency, and and because you have such a wide scale, right, at which these things are interconnecting, these are characterized by links that are narrow. Typically, you're going to have 4 lanes. I've seen some 8 lanes, but typically 4 lanes, right? Ethernet, for example, right? I mean, those are all 4 lanes kind of thing, right? I mean, you got 112 gig, which people generally call it 100 gig, right? So 4 of them, the encoding overhead, once you take that out, it's really 100 gig. 4 lanes, you get 400 gig networking connection. It's moving to 224, but 200, right? I mean, that's what people say in common passing terminology. So each lane is 200 gig, then it becomes 800 gig networking connection. But it's like, narrow and super fast. If you look at just the PHY latency by itself, forget the rest of the stack, right? It's huge. Right, when our networking moved to FEC, the FEC itself added 100 plus. When I say 100 plus, it's actually in reality 150 plus nanoseconds on the latency. And the PHY by itself, if you didn't have the FEC, if you look into standard implementations across the industry, those are 20 plus nanoseconds. Contrast that with the latency sensitive one. So if we go back into this picture here, right, within the rack, remember that there was a chassis within that, right? This is like a chassis. So you got CPUs, 2 CPUs connected. I didn't show the memory here, also another picture. And then you got some SMP cache coherent links. You got PCIe, you might have CXL. Within each of them, you can again have an MCP kind of picture at an SoC level, package and die. We're not going to talk about that. We're going to stick to somewhere over here and here. So these are the ones where you got today literally in a platform. If you look into a 2-socket platform, you got, when I say hundreds, it's really hundreds. Right? There are hundreds of lanes. Right? CPU to CPU connectivity can be in hundreds of lanes. And then, there are a bunch of IOs that are connected. And, it's not uncommon to see today's CPU packages come with 64 lanes. Some of them come with 128 lanes of PCI Express. So, basically, people want to, so if you think about what a server looks like, it's going to have very powerful networking connectivity, like a NIC. So that will be one PCI socket, 16 lanes, right? You're going to have there. You're going to have some SSDs connected to it. So, and then you're going to have some, GPGPUs. People want to put many GPGPUs. Each of them is 16 lanes, right? So, 2 CPU sockets, people can put 8 GPGPUs in there. So you can quickly, the math adds up, right? You're literally in hundreds of lanes. So what happens when you're in hundreds of lanes? When you're in hundreds of lanes, you do not have the same liberty in terms of cost, in terms of area, in terms of power, in terms of even backward compatibility, because you are catering to a broad range of the ecosystem where people are basically innovating, right? There are multiple companies doing SSDs, there are multiple companies doing GPGPUs, there are multiple companies providing networking solutions, and that's not all, right? I mean, there are a lot of different companies, as you will see how many companies are there in the PCI Express ecosystem. So you need to be backward compatible. Not everybody is moving on the technology transition at the leading edge. Some of them will be, when you see some people moving to Gen 5, a lot of them will be still in Gen 4, some will still be in Gen 3. And then, that move, it's not like, you turn the switch one fine morning and everybody is in the latest and the greatest technology. So the technology needs to be fully backward compatible. Latency, extremely important for these load-store interconnects, right? If you're talking about cache coherency, if you're talking about memory access, every nanosecond counts, every nanosecond. And we have been flat in terms of the latency through this entire technology transition. We just cannot afford to add latency. So these kind of FEC latency adder, it's just a non-starter for us, right? I mean, we would go to hundreds of links and twice that many instead of changing these speeds to these higher numbers. So we'll talk about more in the requirement section, but basically, if you look into, and by the way, the less than 10 nanosecond, people have varied numbers. I've seen all kinds of numbers. When I say single digit, it's all kinds of numbers in the single digit. Those that really deeply care about the latency, their single digit is really low single digit, okay? But if you're doing like an SSD, for example, right? I mean, you can be 7-8 nanoseconds. That's not the end of the world, okay? But if you're doing like cache coherent link, if you're doing something like a CXL memory access, those latencies, they matter, and they matter substantially. So when we go for these higher data rates, we cannot, basically, we are looking at a flat latency. So the FEC by itself has to be in the less than 1 nanosecond or less kind of range, right? So, with the latency sensitive LoadStore IO moving to 64 gig with PAM-4, we need to have a lot of innovations to make sure that we meet these latency, area, and cost challenges. So again, stepping back a little bit in terms of, okay, what is LoadStore IO? I talked about LoadStore IO. What is a LoadStore IO, right? So it's basically, it's a hard thing. I get asked this question, and it's a very hard thing for me to define very precisely, but I'll make an attempt, right? It's basically the ability to directly access memory, whether it is coming from a CPU or it is coming from an IO device, right? So you got the notion of memory, you got the notion of a memory address space in the system, right? When you say, hey, load address X or store to address X, it's a direct load store that you are doing. So what happens there is that if it is going across a link, it basically shows up. If you look into PCI Express specification, there are things like memory read and memory write, and those are really memory read and memory write transactions. So the memory gets mapped into the system address space. So this is a typical 2-socket server. You got DDR memory hooked on there. This will be like a CPU to CPU cache coherent link. By the way, those are all run today on PCI 5. For us, this will be like the QPI going to UPI, ultra-fast interconnect for us as an Intel. You've got, the PCIe channel coming here, and then you've got a connector. I showed by 16, can be by 8, by 4, by 2, by 1, can be anything. And you plug in your PCIe card or your CXL card in there. And, these cards can be like your GPU, they can be your NIC, they can be your, SSDs, they can be anything. Or if that's CXL, they can be a CXL memory device. So these are all open slots, right? People are innovating, they're going to connect. So, and these ones are going to work in anyone and everyone's system, right? This can be an Intel system, it can be our competitor system. If you are designing these cards, they work across the board, right? That's the way the specification is defined. So the memory can be mapped, whether it is memory attached here or it is attached here into a coherent space or a non-coherent space. And typically your PCIe accesses, not typically, PCIe accesses are non-coherent. They don't have coherency semantics. CXL defined cache coherency in the semantics. It basically runs on PCI infrastructure, as you can see here, but you can see there is a cache and the mem. So it basically has got some amount of coherency and memory semantics built into it. And they're all basically, this is the other key characteristic, right? Where it is different than networking is that transactions are guaranteed to be delivered and completed in a reasonable time. There is no notion of a lost packet. Lost packet causes bad things to happen in a system, because if I have a, if I have a cache miss, I'm trying to, I'm waiting on something to execute my instruction, and you've got lost packet, that causes that has serious consequences for us. So no dropped packet, Given that these are direct load store, you cannot rely on a software-based retry. Typically, you got hardware retry, and all of them have some form of ordering, like or cache coherency. In other words, there is a notion of an order of the transaction. So, for example, in this picture here, if I write the data, doesn't matter where I'm doing it, whether it is from a CPU, whether it is from a GPU, right? The device can be anything here. If I write the data and I post a flag saying the data is ready to be consumed, if you read the flag with the updated value, you're going to go and read the data. This data cannot be hanging somewhere in the network, and you cannot be reading stale data. So the ordering becomes important there. And in general, because it is load store, there is a very explicit timeout and error reporting hierarchy, because we want to make sure that one bad actor does not bring down the entire system, right? So there's a bunch of hardware-based error containment guarantees that are built in. So that's very in short, what is a load store kind of interconnect. So what is PCI Express? PCI Express at a higher level is a layered protocol, and I've showed the layers here. So let's start from here, and then we'll come to the mechanical and the software here. At the very bottom layer is your electrical layer, and then there is something called a logical PHY. Then you got your data link layer, then you got your transaction layer, and then you have software layer and mechanical layer here. So the software layer is the one, and you can see there are configuration registers that are attached with each of these layers. So software basically interacts through the hardware using these configuration registers, right? If you want to tell the hardware to do something, the mechanism is you go write to a config register, or if there is something, let's say an error event that is happening, the way you know it in software is you go and read the register, right? So these are there for software is PCIe. It has got PCIe compatibility. So about 2 decades back, we moved from bus-based to SerDes-based infrastructure with PCI Express. Our software still is PCIe compatible, not hardware, but software. Right? Still the bus-based. If you have that old software, it will still work on PCI Express. That's how seriously we take backward compatibility. Configuration based. Like I talked about, there is typically a PCI driver, because you can't expect all the OSs to know about all the registers. So there is a PCI driver to abstract those things out. And PCI Express has also something called an enhanced configuration model, where these registers can be mapped into the memory map space. So bunch of great work that has gone on there. Transaction layer, this is, as the name suggests, it's about transactions. So, you want to send a transaction saying, hey, I want to read this location, or I want to write to this location, right? I mean, read, write, things of that nature, right? Or you can pass a message to somebody. So these are what are known as split transactions. Split transaction means that, I'm going to send a read, I'm not going to wait. I'm not going to keep waiting on that read to come back before I issue the next transaction. I'm going to issue a bunch of transactions. They come back whenever they come back. So they're all packet-based protocols. The flow control is credit-based on a hop-to-hop basis. So in other words, there are different types of transactions. They go in what we call different flow control classes. So you need to have the right credits to send it. So that way, I'm not saying, oh, my queues are full, can you hold up, right? This is a link. So, you just do everything credit-based, everything is inbound-based. Then there are virtual channels to ensure quality of service, right? So for example, you don't want to mix different traffic types. You maintain different virtual channels so that each gets its own fair share, so to speak. Link layer, this is important. It's the logical connection between devices. This is the one that ensures that the packets got delivered reliably. Remember what I said, no lost packets. Right? There's no software to come, and there is software to come to bail you out, but that means bad things have happened, right? So that's a lot of the error current containment stuff will kick in. So you really do not want that to kick in as much as feasible, right? That gets basically counted against what is known as failure in time, right? And we try to keep that, and you're going to see that metric. We try to keep that extremely low. So it's reliable data transport. And this one is just a physical layer, which is, all the encoding stuff, anything that you need to do to make the link really run faster, all the SerDes stuff, all the circuit stuff, all of that is encompassed here. PCI Express does one protocol, one stack, but we support multiple form factors because we are a ubiquitous IO, and as we will see, so we basically we support multiple form factors, but one protocol, one stack, same silicon works across all market segments, unlike a lot of other standards, right? I mean, standards do things based on the segments that they serve, but for the segments that we serve, that's a critical requirement for us. Quickly, PCI SIG, founded in 1992, is the one that basically is in charge of PCI Express and 830 plus members, so paid members, right? So it's an open consortium. There is an annual fee, and these are all these companies that are innovating on PCI Express, so that's why they are members. PCI SIG. So now let's talk about evolution of data rates in PCI Express. So PCI Express, you can see the picture here or the table here. They represent the same thing. We basically, every generation, we double the data rate. If we are not doubling the data rate, it's not interesting for us because the ecosystem is so huge, people have to recoup their investment, right? So when we make jumps, we make substantial jumps, which is 2x. So you can see that, we started at 2.5 gig, 8-bit NV encoding, 5 gig, 8-bit NV encoding. You will notice that when we went 3.0, we went to 8 gig. We changed the encoding. And the reason for that is, at that time, based on, so normally whenever we do these kind of transitions, we look into what is the, or we try to project, right? Where do we think the broader ecosystem is going to be there? Every system that we talk about, right, from PC to handheld to workstation, all of them have PCI Express. So, and we don't want to leave anybody behind. So it's very cost sensitive and all of that. So back then when we did the analysis, we said, okay, hey, 10 we can do, but few things have to give. Either the reach of the channel has to give. Up until then it was 20-inch 2 connectors, right? Or the power has to give, right? And neither was acceptable to us. So what did we do? We said, okay, hey, let's sweep. Let's see, where do we meet the requirement? And again, over time, these numbers do change because people do come up with better materials, better board materials, better packaging materials, and all of that. But you have to project in terms of when you expect the technology to start intercepting, and will the broader ecosystem of your 800 plus member companies be really ready to make the transition in a cost-effective and power-efficient manner, right? And the answer came back as no. Or the other thing that had to give was we had to say to the server guys that, hey, sorry, you either pay one of these or you don't make the move, right? And none of them are acceptable to us. So we said, okay, 8 we can do. If we do 8, what we need to do is now just get rid of this. And it's a big move, but we are willing to do those moves, make those moves, because we want to make sure that the technology remains true to its characteristics, right? So we went to 128, 130 encoding, and now we are in 6.0, 64 gig, PAM-4. We're going to talk about that, flit mode. So the beauty of backward compatibility is that if you take a by 16 Gen 5, which is 32 gig, it's going to interoperate with a by 1 Gen 1 device at 2.5 gig. That's the promise of backward compatibility, seamless interoperability. 20 decades, 6 generations, fairly impressive. My personal take is 1 decade, 3 generations is a success story. This is more than a success story. This is wildly successful, and knock on wood, hope this journey continues. So what are driving this bandwidth, right? And as we saw in the previous picture here, you will notice that, off late we are getting pushed to drive the bandwidth faster. It's not because, we like to move for the sake of moving, right? I mean, as I said, we move whenever we sense that there is a need. When there is a need is coming, we make the move. So that way, we are not too much behind. We also don't want to be too much ahead, right? It's basically, all of these proliferations that are happening, the ones that I talked about, cloud. I mean, a lot of innovations are going on there. Artificial intelligence, a lot of innovations are going on there. People are inventing all kinds of things, right? Whether it is networking, whether it is FPGAs, whether it is accelerators, ASICs, people are putting memory on PCI Express. There are alternate protocols, as I showed earlier, which is our QPI, CXL, they're running on PCI Express. They all have an insatiable need for the bandwidth. Basically, your compute power is growing, whether it is standard CPUs, whether it is GPUs, whether it is purpose-built ASIC, it doesn't matter. Your compute power is growing tremendously. And when that happens, the demand for the bandwidth goes up, right? You got to feed that beast, right? You got to move that data between them, right? You can't be computing in one place and not pass the results somewhere else, right? And they're working very collaboratively. If anything, there are people are increasingly deploying different types of compute engines for different purposes, so data has to keep moving between them. And we have already added 128 lanes. There is not a whole lot of room left in the board to route these wires, right? So there is one thing that has to go up, and that is speed, right? And that 7 years that you saw between Gen 3 to Gen 4, while we were trying to figure out how to make that transition, right? That was a big leap. People grew the number of lanes, and that's how we got around it. But now that's taken, so we have to keep out innovating our needs, right? So. And again, I might sound like a broken record, but all of these moves have to happen with all of this: cost, performance, power, and carry all the segments with you, right? All of those are must. So, and we are always up for the challenge. So this is basically the requirement table, right? And it always helps us to put these requirements. Otherwise, you end up getting different things from different sets of people, and you move in all kinds of directions, right? It's always good before you go to something to give the guardrails. These are the guardrails. And we, as I said earlier, before we get started, we always put the guardrails in. These are the guardrails we have to meet. Data rate, of course, 64 gig. PAM-4, you can argue it's not a requirement, but if you were to meet these other requirements, that's the only option left. So we have to double the bandwidth. No compromises there. The latency adder, we need to less than single-digit latency adder is acceptable for PCI Express. I'm not going to talk about CXL and UPI. Those are basically zero latency adder. And I did have a talk on hot interconnects in terms of how I have some thoughts in terms of how to do zero. We're using the same approach that we talk about here. That's very feasible. So, and as you will see that most of the cases in PCI Express, the latency adder, we actually gain back latency. In other words, it's a negative latency adder for us, not a positive latency adder, which is a good thing. We don't want to give up on the bandwidth inefficiency. I cannot afford to give 12% for the FEC overhead. That's just not happening. Less than 2% adder over, I didn't have FEC in 32 gig. If I put FEC and another CRC or whatever on 64 gig, I'm not getting 12% of bandwidth for those extra bits. I need to make sure that my overhead remains less than 2%. Reliability is measured for us in FIT, which is the failure in time, basically number of failures in a billion hours. We want it to be, there's nothing like a zero FIT. We love zero, but probabilities in real life, errors will happen, and you never get a zero probability, right? But we want it to be close enough to zero and substantially to the left of one, right? So some real small fraction. And just to give you an idea, most of the silicon, if you look into it, their FIT is in 3 digits and 4 digits. So basically what we are saying is that the interconnect contribution to that FIT is practically zero. Channel reach is similar to 5.0. Cannot say that, hey, go 2 inches and put a retimer or something like that. We got our keep out reach, and especially if you're putting hundreds of those lanes and putting tens of cards on a platform, there is no way you can. We have done the channel reach part in the past, and we might have a little bit of leeway, but not a whole lot. Power efficiency again, can't burn power, more power, so it has to be better than 5.0. Need to have a very good story in terms of low power. We want to aggressively go to low power state because nobody is getting extra power. Well, we do get some extra power as we are processing more, but it's not really commensurate with the amount of performance that we are getting, right? So I did talk about plug and play. Full backwards compatibility is really, really, really important for us. And of course, we want it to be high volume manufacturing ready, right? I mean, these are in millions and millions and millions of systems, right, are shipping every year, right? So it is, when we say high volume, it is really high volume, right? Everything from your handheld all the way up to the servers, right? Everything has got PCI Express. Very cost effective, scalable to hundreds of lanes in a platform. In short, tight space that we find ourselves in to meet all of these requirements, but none of these are negotiable. Alvin, with that, let's take a brief pause and see if there are any questions. I think, yeah.
Sure. one question that came in. Does CXL versus PCI Express perhaps fracture the compute sector?
It does not. So what CXL does is, CXL is built on top of PCI Express. So if you are a CXL device, you have to run the same PCI Express PHY, the same PCI Express protocols, right? It's built on that. What you added on top of that is some coherency semantics. It's in addition, right? And you added some memory semantics. So what effectively what you're doing is that non-coherent space that PCI Express is in, you are allowing devices to cache the data in the system, which with PCI you cannot do. And by the same token, the memory that is attached to CXL device can be cached by other caching entities in the system. So it doesn't fracture that system, again, because of that symbiotic relationship. What it does is it does enable devices to become even more powerful on a PCI Express based PHY and PCI Express infrastructure with all the CXL semantics that comes into play.
Got it. Another question related, you talked about the power efficiency of PCI 6. The goal is to make it better than PCI 5. What, from your experience, what is the minimum technology, CMOS technology node you would need to achieve the performance as one, but also with the power efficiency? Normally,
I really cannot go through a lot of the process kind of stuff here, but if you, let me state in this way, right? The industry is at it's out innovating in the process technology node side. Most of these, from a PHY perspective, as we all know, PHY doesn't get as much of benefit from the process node string, right? I mean, it's the logic that gets the benefit, and even that's also not there are challenges in that scaling. Most of the things that we do here apply for all of those process nodes that are that you can see. So we do make sure that things that we are doing, for example, for us, it will be in the N-1 or N-2 generations. If you choose to put this PHY in there, you will still be able to achieve all these goals. What happens with the N-2 or N-1 node will be that, the rest of the logic stack that we talked about, the transaction layer, the link layer, and all of that, those gates will become a little larger because the gate count there will be larger because you're not shrunk as much, right? But yeah, it's all, these are not non-issues as far as the goals are concerned.
I see. So you're thinking there's no need, for instance, there's no need to even go to a FinFET technology, say starting at 22 nanometers.
22 is a given in this time, right? I mean, yeah. I mean, I'm thinking more if you're, let's say, do you really need to be at the 3 nanometer or 5 nanometer kind of edge? You don't need to be.
Sure. Okay. Okay. I mean, there are fewer and fewer companies going into the very, very most advanced nodes due to cost, right? And so, I mean, Intel's obviously a very, very privileged position where the products make sense, but I was just curious. Yeah.
No, this is for the broader ecosystem, 830 plus member companies. So, you can expect that people will be in all the different types of process node. And yeah, we don't do anything that's going to jeopardize that adoption.
Got it. Okay. Well, actually, let's continue with the presentation. We'll take more questions towards the end. Thank you.
Yeah. So let's talk about PAM-4 and some of the assumptions, right? And this is where I would assume that people are very familiar with it, but very quickly, PAM-4, what you're doing is that you are basically, your frequency, your Nyquist frequency is still the 16 gig that we had as with 32 gig, right? In other words, within the same UI or unit interval, you are now encoding 2 bits. You're basically splitting the voltage as opposed to making your time half, right? Same time, same unit interval, but splitting the voltage. And that helps with the channel loss, right? I mean, that's the cost part of the equation, cost and power part of the equation. What it does is, because of the reduced eye height and eye width, we are susceptible to errors, right? So we will deploy a few techniques here in order to minimize, but as we will see, right, I mean, errors are going to be a huge problem. for us to solve. Right? You can see that consecutive voltage levels are gray coded, so that way any error that happens affects one bit. The most likely error case would be you move across a voltage level. We also will deploy pre-coding in order to minimize errors in a burst, especially if you have done like a DFE kind of an implementation. You can expect an error burst with these kind of high bit error rate and voltage shrinking. So there is a pre-coding mechanism that's well established that will be deployed by those, and you can request pre-coding or not request pre-coding. And as a transmitter, you must satisfy a pre-coding request, but as a receiver, it's your choice whether you request it or don't request it. So those are some of the techniques we will deploy, but bottom line here is with PAM-4 signaling, as the networking guys have seen, right? I mean, error rates are huge. Some of the error assumptions we talk about are around the burst, right? So we have something called first bit error rate. So this is the raw bit error rate. So the probability that you're going to get an error the first time. Now, whenever that happens, I can, because of the DFE, I can have that error burst keep moving to the subsequent UIs. And that's a burst error in the lane. You can also have correlated errors, right? Some common noise sources in the platform, like power supply noise and things like that. So because of an error here, you can also get an error in a neighboring lane, in a multi-lane link. And we basically, as you'll see, that we are going to deploy a bunch of techniques. But on the DFE side, what we have done is that we have constrained the DFE tap weights in the spec, so that way we can minimize this burst. And then the correlation across lanes, that's something that we just have to deal with. And effectively, this is the raw BER would be a combination of all of this, but we are going to count all of this as a single error for the error count kind of point of view, right? I mean, in reality, you are going to end up with multiple errors. We just expect that the mechanisms that we deploy will be able to handle this. So we are going to deal with things in terms of those, right? So this is a big difference here between what networking does and what we do. We have two mechanisms to correct errors. We didn't have FEC in 32 gig. Now we are going to add FEC. So that, of course, does error correction, forward error correction. We have link level retry, right? Remember that when I showed the initial picture, I said that, no lost packet, nothing, right? I mean, packet delivery has to be guaranteed. And the way we do that is through link level retry. We're going to basically deploy both of them to correct errors. So the characteristics of the FEC is that your latency and complexity increases exponentially with the number of symbols you correct. So if you assume a symbol is 8 bits, which is easier for us, right? Because again, we are latency sensitive. I cannot have a 10-bit symbol, okay? Then I'm going to look at substantial amount of multiplexing in the logic that we have, right? Which means latency gets added. So if I do that, and then let's say if I correct k symbols, right? Then I get, if my flit has got n symbols, then it is like n choose k, and then I'm going to have 8 to the power k. 2 to the power 8 to the power k, right? I mean, that many different syndromes that I need to deal with. So it's an exponential increase, and that's the reason why FEC latencies are very high, especially if you try to correct multiple symbols. Detection, on the other hand, it's a linear problem, right? All that you're doing is you're checking whether your syndrome is 0 or it is non-zero, right? It's just a linear problem. You check are the bits 0 or not, right? And what happens on the detection is that you can ask the other side to replay the packet, right? And that's how you get around the error. So we're going to deploy both of these mechanisms. And the metrics are a performance metric, which is the probability of retry or the bandwidth loss due to retry. And the other one is called FIT, which is the failure in time. And we'll use both of them. We want to, again, emphasize on low latency, low complexity, and keep the retry probability an acceptable level so that there is no performance impact, and low bandwidth overhead. Remember, less than 2% overhead, right, over fast channels. So all of these are important features, and here is our approach. This is a busy graph here. I wanted to focus on two. And when I did the initial analysis, I did it for 648 bytes. Of course, our flit size is different now, but it doesn't matter. The conclusions are still the same. This is the raw FBER, right? And this is the, let's say in this side, it's the probability of retry. So notice that if I'm at 10 to the power minus 4, which is basically where the networking standards are, if you're at 10 to the power minus 4, your probability of retry is somewhere around 10 to the power minus 2 with a single, if you can correct a single instance of error, okay? FPER, remember that's like the whole burst, right? If you can correct everything in that burst, your retry probability is 10 to the power minus 2, very unacceptable number, right? So that's the reason why, networking, deploys things like 15 symbol correct and stuff like that. And they don't have retry, link level retry, as far as I know. And then if I do 2 symbols, I get 10 to the power minus 3. So, at 10 to the power minus 4, this is a slow climb, right? In other words, I have to have a lot of symbol correct to get to anything acceptable level. Move to 10 to the power minus 5 or 10 to the power minus 6. Now you can see that, now I'm at, even with a single symbol correct, I'm somewhere around, 10 to the power minus 6 kind of number. So what's happening, right? Basically, this is improving exponentially, right? I improve here by 2 orders of magnitude. I'm getting a 4 order of magnitude, 4 or 5 order of magnitude. It's getting better. And that's again, if you do the probability calculation, that becomes fairly obvious, right? Because it's an exponential nature. So we target for PCI Express, we are targeting 10 to the power minus 6, not 10 to the power minus 4. Okay, so that's critical for us, right? And that got debated a lot, right? As you would expect in a consortium. The downside of minus 4 versus minus 6 is a couple of inches probably on the motherboard of channel loss, but you're still within the table that I mentioned, right? It does tighten up things a lot for the designers, right? They don't like that. They like to have the flexibility, but then it's a non-starter for us, right? So 10 to the power minus 6 is where we are for PCI Express. So that's point number 1, right? So that's the first trade-off that we did, right? Or the first engineering, you can call engineering judgment or whatever, right? All of course data-driven, right? In terms of picking the right parameters. So with that, what happens is that what we say is that if we pick 10 to the power minus 6, I can basically get a very lightweight FEC to the point where my FEC latency is going to be really, I don't care. And then I can rely on a link layer CRC, right? That's basically the approach we are going to take. So the other thing with PCI Express is that the packet sizes are variable, so they're not naturally flit-based, right? Unlike things like on the CXL side, right? When you're doing CAS and MEM and coherency kind of thing, those are all flit-based, which is flow control unit. That's what it stands for. It's a fixed size, basically, right? PCIe has got variable packets, and so we had things like things that would signal where does the packet begin, where does the packet end, all of that. That doesn't work well for a variable size packet. Doesn't really work well for error correction. Well, I suppose you can do that because you can have multiple tiered of error correction. First, you can correct errors and say, hey, where does your packet really end? You make that robust. And then you can have a hierarchical kind of thing, but then you end up losing a lot of efficiency in the process. So second move on PCI Express side, we move to a flit-based mechanism while remaining backwards compatible. So flit size for us is 256 byte. We will do a FEC on that. Once you do a FEC to correct error, then the error detection and the retry also needs to be at the flit level, because it doesn't make sense for you to correct at this level and then do that detection at a sub level, or your detection of the subsequent error happen later on, right? It becomes a nightmare to manage and very inefficient, right? So once you do correction at the flit level, it's only logical that you will do detection or the CRC. They will be at the flit level. They will be not on a per transaction basis as they have been in PCI Express in the past, which means that the retry needs to be at a flit level, not at a transaction level, unlike in the past in PCI Express. So these are substantial changes, not big changes, but substantial changes in the philosophy in which PCI Express does packetization. But at the same time, I don't want to give up. Remember, I'm all about backward compatibility. I'm not giving up on the different size TLP. What I'm going to do is that notice that within this, to 236 bytes are for TLP. So within that, you can have your variable size TLP. So in other words, you have basically given them a slot within a flit, right? 236, the first 236 byte is for you, the transaction, right? Variable size transactions, whatever, right? So what in the past, in the link layer in the layering approach, the link layer would put in a CRC. Guess what? We're going to have a parallel link layer now. It's going to put this flit-based CRC. The upper layer is still the same. It still does its variable packet. So 236 bytes for transaction layer packet, 6 bytes for data link payload, right? So earlier it used to be a separate packet by itself. Now we are saying, hey, no need for that. And there is a reason for that. And I'm going to talk about that in a minute here, but 6 bytes dedicated for data link packet. To protect that, earlier we had 32-bit CRC. Now we have 8-byte CRC. This is fairly robust, right? 8-byte CRC, read Solomon code base. So guaranteed to detect up to 8 symbols. And beyond that, your detection probability is 2 to the power minus 64. So practically nothing is going to get through that in terms of your fit. And then we got the forward error correction. And for the forward error correction, what we did in this 256 byte is that you will notice that it's a 3-way interleave. The 3 colors are the different ways. So all the blues are a FEC group. All the oranges are a FEC group. All the greens are a FEC group. And you will notice that along any wire, you are not going to have the same color appears 24 bits later, right? So what it does is each of them is an independent FEC group, and you will see that there are 2 bytes of ECC, right? So basically it's a single symbol correct, 3-way interleaved. So any burst you get, as long as that burst does not extend beyond 3 symbols, we can correct that error. And that's the earlier comment I made about, hey, we are going to constrain the DFE taps and all of that. So the probability that a burst due to DFE is going to extend beyond that is significantly less than the FBER itself, right? In which case, sure, there is a probability, but if it is less than the FBER by itself, you are contained within that FBER probability in an order from an order of magnitude perspective. Because of all of these, some of the benefits that I get from earlier side is because these are overheads, right? I mean, these 6, 8, and 6, these are overheads. In other words, I only get 236 bytes of useful stuff over 256 bytes, right? But I have no sync header, I have no framing token, and I have no per packet CRC. And you will see that basically this results in a better amortization, especially for small transfers. And the flit accumulation latency, if you are a by 16, it's going to be 2 nanoseconds. I cannot do anything till I accumulate a flit. 8 nanoseconds for a by 4, 16 for a by 2, and 32 for a by 1. And notice that I got explicit DLP here. So what it means is that the first 2 are dedicated for an ACK or an NAC. So if I receive a packet, the new spec is it tightens things around, says that if you got a packet at time t, the first bit shows up on your pin. The ACK or the NAC on the other direction coming out of your pin in a by 16 must show up in 50 nanoseconds. So we are tightening the latency from the spec point of view, because if there is an error that the FEC cannot correct, and it's a weak FEC, right? It's a lightweight FEC. So we want to just make sure that the retry happens fast enough, right? And we are tightening that around it. And in order to do that, we are not going to, we are going to make sure that, in every flit, you have the opportunity to say whether it's an acknowledge or it's a negative acknowledge. Right? Negative acknowledge means I got an error, please send me this packet again, and or flit again, and the other side will do that. So we're trying to do the replay latency effectively in 100 nanosecond for a by 16, and if you're a by 1, of course, you've got a lot more accumulation time. It still is significantly less than 200 nanoseconds is what we're going to put a spec guarantee at, right? And effectively, that's basically what improves our performance. And by the way, the other 4 bytes are for credit management and stuff like that. So because you're exchanging credit, you're not really, don't have to schedule a credit exchange. That reduces our area substantially. So with all of these, with the doubling of everything, if you do the analysis in terms of your storage requirements, actually storage requirement goes down, except that because I need to be backward compatible, I will have the same storage requirement as I had in Gen 5. In other words, I didn't add anything. So this was a replay kind of thing. So just in this example, if we look into packets that are going from device A to device B, in this example, they go through a retimer. Doesn't matter, the retimer doesn't participate in the packet. So, flit 11 got an error that could not be corrected by FEC. So CRC figured that, hey, there is an error in this particular flit. But we are not going to ask for a replay, because the next flit, there is an indication saying, hey, the prior flit was a no-op flit. So the device will wait and not just pretend as if this didn't happen. In this example, this had an error. And then in that case, I'm going to ask for a replay of only that flit. So later on, this device replays only that flit. So after flit 13 gets replayed, we go back to flit 17. Now, here 18 and 19 got an error. So, device B could have asked for a replay of 18 and then replay of 19. But in this case, it's easier to just say, hey, replay from flit 18 onwards. I should have said from 18 onwards, not 19 here. And in that case, you're going to replay from 18, 19, and 20. Right? So there are two types of replay mechanism. This type is what is known as go back N, and that was there in PCI Express before. This is known as a selective replay. We introduced this in 2.0 for efficiency reasons. In this calculation, you'll see that I've swept the number, but basically, all of our PCI Express spec is at 10 to the power minus 6 FBER. So these are the numbers, right? And you can see the other numbers for comparison purposes. As you can see, if we are at 10 to the power minus 4, it was a no-go. But with 10 to the power minus 6, my retry probability of a flit is around 10 to the power minus 6 by itself, right? Or whatever, closer to 10 to the half a bit in 10 to the power minus 5 and 10 to the power minus 6, which is a very reasonable thing, right? The simple question to ask is, hey, would you rather pay 150 nanoseconds of latency for every flit, or would you pay that 150 nanosecond every 5 times 10 to the power, or if I did my math correctly, 2 times 10 to the power 5 flits, right? Around 10 to the power 5 flits. Would you pay that 150 for only that flit that might get an error? And of course, I'm going to choose the latter. Retry probability over retry time. This is the percentage of bandwidth loss, so 0.05%, which is fairly reasonable. It's not, it's not even measurable in terms of your real bandwidth loss. And the fit, as I said, we want it to be close to 0, and we are at, this is as close as you get to 0. It's a non-issue at that point, right? So we do meet those performance and reliability requirement with even with a lightweight spec. And with a strong CRC. Without that strong CRC, we would not be in this fit. If we stayed with the 32-bit CRC, this would be like an unacceptably high number, right? So 6 bytes kind of gets us over there, but we wanted to be, there was no need for us to save another 2 bytes if you look into that arrangement. So we just throw in the extra bytes for more robustness. This shows the bandwidth scaling in terms of, how well do we do. And remember that, if I go from 32 to 64, I expect to see 2x, right? And then I said that up to 2% inefficiency I can take, so maybe 1.98 or something like that, right? And in some cases, we are a little bit below that, but notice at the cases that a lot of the cases, we are significantly above 2 actually, right? 2 is somewhere over here, right? So all the way up to 128 DWORD, which is 512 byte. DWORD is 4 bytes, so 512 byte payload. We are either the same or much better than what we were before. In other words, if I'm operating here, I get close to a 3x improvement in my effective bandwidth, right? And that's because of the better amortization that we have. And as the packet sizes become large, that amortization reduces, so your benefit doesn't show up, right? And then if it becomes large enough at a point where you start hurting actually, right? Going from Gen 5 to Gen 6 in terms of bandwidth efficiency. Now, the flip side of this argument is, what do real systems do, right? PCI Express does allow for up to 4 kilobyte max payload size, but we used to be, typically your systems will be at around 256 byte max payload size. So your operating point is somewhere from here, either here or here or here. That's your max payload size operating point typically in systems. So realistically, we come out as the winner, right? Although if you were to argue that, hey, in some cases you might lose maybe at around 1.9 instead of a 2x, that's fine, and that to us is an acceptable trade-off considering everything else. So much better efficiency, small packet payload. The great thing here is that small packet payload, which is, if you look into a lot of the networking traffic, it tends to be very bimodal, a lot of small packets, like 8 byte kind of packets, right, which will fit somewhere over here, and rest will be like 64 bytes, so which will be over here. Tremendous gain. So this one is showing the latency. The way to read this table is, again, this is the payload size. So, and this is the, at 32 gig, what would be your latency? And this is showing, how much would you add or what the latency for accumulation would be with 64 gig. So positive number means I'm adding latency, negative number means I'm taking latency away. So you can see that most of the cases, I'm gaining in latency, I'm not losing in latency. And by the way, I didn't even count any of the expected latency savings due to removal of the sync header, fixed split sizes, and all of that. If I count that, realistically, I will be getting closer to at least 7-8 nanosecond of gain, right? So if I subtract 7-8 nanosecond, this will go down even substantially. And so it's a net benefit, right? Basically, what happens is that with flit mode, a lot of the muxing and everything goes away. As a result, you're going to get so much of latency savings, right? I mean, if you have to do, for example, CRC on a fixed payload, that's a lot better than doing CRC over a variable payload, right? Because then you are going to look at all kinds of permutation combinations that are possible, right? So overall, meet or exceed the requirement in this particular one. So now let's look into, how well did we do, right? So of course, data rate, we are going to meet 64 gig, otherwise we won't be talking. Latency adder, yes, some cases where we can be up to 10 nanoseconds, but for the most cases, we are going to get latency savings, not paying in terms of latency, so which is a great thing. Bandwidth inefficiency, we exceed, right? So in a lot of cases, we are getting greater than 2x, which is a great thing for us. Fit, we saw that was around 10 to the power minus 10, somewhere in there. So, not at all an issue. Channel reach, of course, we are meeting the channel reach. Power efficiency, now I want to say something, and Alvin was asking the question that, hey, are all of these dependent on the process node and all of that? Yes, it depends on process node, it depends on your design style, right? I mean, you can make a design that's fairly inefficient, or you can make a design that's fairly efficient. But from a spec point of view, we design it and we define the spec in a way where you can achieve it. And looking at a bunch of things that are going on in the industry as well as our own, I'm fairly confident that we will meet these requirements. Same thing on the low power. I didn't have time to talk about L0P. I knew I won't have the time otherwise. We are introducing a new low power state called L0P. What it means is you can have some lanes active, other lanes sleeping. So for example, if you have 50% bandwidth need, you can have 50% of the lanes active, the other 50% of the lanes can be sleeping, and so on and so forth. And you can modulate your link with dynamically without impacting traffic in flight, right? So that's I'm pretty excited about that. That will save us a lot of power in the long run, and full backwards compatibility. And of course, we will, given the market segments we play in, we do expect it to be high volume manufacturing, cost effective, scales to 100%. So, in conclusion, right, spec wise, we are at 0.7, 0.9 is imminent, going to come out shortly. Been very challenging in multiple fronts, but again, right, with the 800 plus member company, and we have the history of delivering and rising to the challenge over the last 2 decades. And as you saw, we are still on track to meet all of these requirements. The LoadStore IO journey continues, and it's 64 gig. Of course, once we are done with 0.9, we'll look into, how does 128 look like, but, it's a little premature for that. But, one thing that I have learned is every single generation, I think, hey, this is, starting with Gen 3, of course, I think that maybe this is the last one, right? But, I hope I'm wrong every single time. This is one of those things where you're really happy that your thinking earlier was wrong. So, and all of these things are dictated by we do proper analysis, because it's a lot really rides on these things, right? A lot of companies it's their baseline. You need to get it right the first time, right? So everything is dictated by simulation, test, silicon characterization, right? This is like bread and butter stuff, right? You cannot muck with this. This is not a one-off standard somewhere, right? Where, okay, hey, that didn't work fine, another 4 lanes I'm going to use somewhere else, right? I mean, this is like you either make it or you have to go back to the drawing board. So, and, but it has got very wide-ranging impact, right, for the entire compute continuum. So, and we take that very, very seriously. So, with that, and as I said, the journey continues, and thank you all for attending. We have some time for question and answer, and I'm happy to stay even beyond the 15-minute mark, past the hour, if there are questions. So, Alvin, let's see.
Yeah. Hey, Debendra, thank you so much for an excellent talk. We have some questions coming in, and just a reminder for folks, if you have a question, please type it in the Q&A box or panel in your WebEx window. Okay, so some questions to start. Do you have any comments on cut-through switching or cut-through forwarding benefits, limitations, concerns as applied to PCI 6?
Yeah, so let's talk about that. So, just to make sure that we are talking about the same terminology, right? So cut-through forwarding or cut-through routing, right, is the notion that on a PCIe switch, I get a packet that's coming in, but without having fully received the packet, I've started forwarding on to its destination, right? In other words, I make a prediction as to where it is going and then start forwarding it. And assuming that's correct, and if I didn't, please retype your question, okay? So actually, I'm going to give you 2 sets of answers. One, what we did in pre-6.0. Remember, I said that my TLP sizes are variable. So if I'm getting, let's say, a 512 byte packet, right? I had to really accumulate that 512 byte packet, check the CRC, then only I know that I could have forwarded to the destination node. Well, PCI Express, in spite of that, right, what we had done back then was we had the notion of where you can do this cut-through forwarding just by looking at the header, even though you have not done the CRC check or anything. You can speculatively start sending it down to somebody else. And later on, when you do the CRC check, if you found that, hey, I got that packet wrong, right? That packet has to be resent to me. But guess what? I've already sent to somebody else. I've started sending it to somebody else. And that's fine. That's not an issue. In the spec, what we had defined was we had defined this notion of something called EDB, end data bad, with that packet. You basically complete that packet, sending it to the wrong destination, and then at the end you're going to stamp something that says that, oh, by the way, just ignore the whole damn thing. So they're going to ignore that, right? And that works, right? Because your error probability is fairly low, so you could do that, right? I mean, it's like every once in a blue moon you're going to get a packet that will EDB. With split mode, actually things become a lot easier. I mean, you still have that EDB construct, but imagine that you got 512 byte, but then my flits are 256 bytes, right? So most likely your 512 byte is going to go across 3 flits because there is a header part to that also, right? And yeah, so as soon as you get your header, and that's good from its split and all of that point of view, now you're even more confident that you can send it. You still have the EDB concept, by the way, right? Even if you got it wrong, so you could do cut-through forwarding with those constructs.
Okay. Next question. Perhaps 60% of the top 500 HPC use PCI Express. for cost and interoperability. So what do you think is the likelihood of CXL converging with PCIe spec going forward?
So, okay, so I think it's like two sets of questions, right? I would say that everybody uses PCI Express. You may not notice it, everybody uses PCI Express. You need to get to your storage at some point, you need to get your networking at some point. Your gateway is PCI Express. There is nothing else that really connects to your CPU, right? What is the CXL and PCIe convergence, right? I just don't see that happening, because even though there is a lot of synergy there, I mean, the caching part, the memory part, and if you look into CXL, the types of problems that CXL is solving, it's very synergistic with PCIe is big, but you don't get better synergies by putting in a kitchen sink in one place. You get better synergies by having focus group do things that they really do well. So who knows what the future will hold, but this is just my personal opinion, and I'm on both sides. I'm in the board side of both the consortium, right? I just don't see that happening personally, and I could be wrong. I've been wrong.
Where do you see PCIe headed in the automotive industry?
In fact, we did we have done several webinars in PCI Express in automotive, right? There are some places where we play very naturally. Things like, a lot of the automotive usages are around, you have to do the storage and all of that, right? Basically, effectively, and the automotive side is going through its major set of architectural transformations, right? Today, where it plays is at what I would call like the node level, right? In other words, anything that you connect to, whether it is Wi-Fi, whether you connect to, your networking within the automotive side of the world, or whether you're connecting to storage, those are all through PCI Express. People are also using PCI Express, for example, for when they do, they got multiple ECUs that are talking to each other. So that nearby, they would put it like through what we call a non-transparent bridging kind of thing. In PCI SIG, we have launched a special automotive work group where we are looking into other usages where we could play. And in general, my personal philosophy is, if there is another standard that does well in a particular area, so be it, right? I mean, we are not going to do something unnatural, but if there are things that are a natural fit for us, while not compromising on those set of KPIs, and of course, in general, we don't like to do something very different or something out of place for a particular segment. There are, like I said earlier, right? I mean, there are different consortia there that are trying to solve some specific problems, and they all have their place, and that's fine. Right? I mean, it's not like everything needs. Every kind of interconnect doesn't need to happen through PCI Express or CXL, right? I mean, that's then we are not going to serve the needs of anybody. But we do look at these things, and there is a special automotive work group that we launched recently, where we are looking into what are the challenges in the automotive segment, things like can we tighten up our compliance program, for example, so that they go through different levels of qualification and all of that. Can some of that be helpful? We're looking into things, some things like node to node communication. Can we do something there? So there are a bunch of things that we're actively exploring.
I see. I mean, with like the weight of the wire harnesses and so forth being such a big factor in the auto application, I mean, auto Ethernet is already, by standard, I guess, uses simultaneous bidirectional, and so PCI Express is, could need a complete facelift, perhaps, to try to deal with something like that, right? I mean.
Sure, and that's what I was commenting. And I've seen actually there is a very good picture about where it shows, two people standing and then all the harness that are going there. Right, somebody had blown up that picture. It's a very telling picture of the amount of wires that are crisscrossing, and yeah, as I said, right, if something doesn't make sense for us to do, we are not going to do it.
Okay. I mean, there's so much electronics, expensive electronics packed in various parts of a car. when will the day come when the car will become disposable once you get a small ding or fender bender, right?
Yeah.
Yeah, yeah. Okay. A couple other questions I want to ask. So your talk focused a lot on the PHY latency and lightweight PHYs, so forth. Has there been any focus on the link layer optimization?
So these are all with the link layer. So if you look at what I presented, a lot of the effectively, right? I mean, a lot of the like CRC replay, which are traditional link layer set of functionality, right? I mean, those have moved converged into this PHY, right? So that will result in even better latency. And the link layer optimization that is being asked, given that we have put like fixed slots, like 6 bytes for DLP within every flit, that will result in a lot of link layer optimization. And you no longer have to go and arbitrate for a link layer packet to be sent, along with TLPs, right? I mean, normally if there is a transaction layer packet that's going to go, right, people will give priority to that because that's doing real stuff, right? Link layer is maintenance stuff, except you need the maintenance stuff to do the real stuff like credits and all of that, right? The way we have constructed 6.0, the flit mode is that everybody gets a slot, right? Different number of slots, but everybody has a certain amount, and it's proportionate, right? And it's all accounted for in the efficiency calculations and everything else that we showed. So yeah.
I see. What about the channel itself, the specking of the channel for PCI 6 versus PCI 5?
So the channel is the same. Now the loss budgets that we allot are different, of course, right? We do expect, there is a certain improvement that we are expecting generationally, right? And that's what I was earlier alluding to, where I say that, in general, we like to see where is the puck going to go, where would we end in the time frame that we are going to introduce a technology. We are expecting certain PCB improvement. We are expecting a lot of improvement on the package side, right? Because if you run at let's say twice the frequency, your loss budget will be double, right? I mean, it doesn't scale, right? So we are expecting a little bit of improvement, incremental improvement all along the way, and with that we expect to meet the channel budget.
Okay, I mean, this is PAM-4, so the Nyquist is still the same, right?
It is the same, but you still get about 9.5 dB extra because of the voltage level. And if you look into our loss budget, those are I think 32 dB if I remember correctly, right? So it still is a substantial portion. So we still expect to get some back.
Got it. Got it. Along the lines of PAM-4, I mean, is the committee exploring like even PAM-8? Does it even make sense?
For PAM-4, we did PAM-4 for 64 gig. The question is for 128 gig, what are we going to explore? We haven't done anything there. Of course, in the SIG context, I'm sure that member companies are doing their own investigation as we have been doing at Intel. And, a lot of these, the data is still premature, but we think PAM-4 with backward compatibility still has legs.
Yeah.
But we'll be looking into PAM-8 also. We are looking into PAM-8 at the same time. It's just that what is the easiest and the most what meets all of those KPIs, right? I mean, it's at the end of the day, it's a data-driven decision, right? And of course, not all the data is available right away. At some point, you have to use a judgment, but it's a mix, right?
Yes. Okay. Hey, and just the last question. The PCI 6 spec itself, is this pretty much what's the state of it right now? And is this something that's available to the public or to the PCI SIG members?
So PCIe 6.0 spec is at what we call right now at 0.71, and the reason we have normally we don't do a 0.71, we do 0.7 and then 0.9. The reason we did a 0.71 is because we felt that there were a lot of changes between what was 0.7 versus 0.9, so that we wanted to get more feedback. So it's like we decided to lengthen the feedback cycle, so to speak. So normally what happens is if there are more changes coming, we would issue something and ask for member feedback, right? 0.9 is coming up imminently. So it's a procedural thing, but yeah, 0.9 will be coming out shortly. Stay tuned. And the difference between 0.9 and the full spec, which is the .0, it will become 6.0 at that time, is basically companies do their IP review, the legal kind of review, and so from 0.9 to the final version of that spec. Spec is not available to the public for free, unlike CXL, but you can buy or you can become a member. So, it's your choice, but and if there are certain aspects that people want to look into, we can talk about how to, especially if you want to do research on something, some aspects, then do reach out to me or somebody else, and we'll see, what can we. You don't really need the entire spec to do what you are looking at doing, right? Certain aspects maybe, and in general, we have been pretty good off late, right, about publishing in peer-reviewed conferences and stuff like that, and journals in terms of what we are doing. So there is enough of data out there, and we have been doing public webinars. So there is a lot of information out there. It's just that the overall spec, which is like 500-600 pages, right? I mean, that's only for members.
When do you expect the first production product to come out with PCI 6?
I cannot comment on that.
Okay, it's okay. No worries, I understand. Okay, well, hey, Dipendra, thank you very much. I mean, obviously, no shortage of questions and interest. Really appreciate your time here, and stay well. And I was going to say, when you come out to San Diego, definitely please let us know. We'd be happy to host you here, and continue to stay well. Okay.
Thank you all very much, and you all stay safe. And it's been a pleasure talking to all of you.
Yeah. Thank you. Have a great weekend.
Thank you.